In the previous lecture, you have seen the gradient of a scalar function in orthogonal curvilinear coordinates. Now, today we are going to discuss the another vector operation which is actually called divergence of a vector function. Actually, gradient is defined, as you know, for a scalar function, but divergence is defined for a vector point function. So, to deal with the divergence in orthogonal curvilinear coordinate system, let us consider a vector point function, or you may say a vector point field f. And actually this vector field f is a function of the orthogonal curvilinear coordinates. And you know, these orthogonal curvilinear coordinates are denoted by the symbol u1, u2 and u3. So you may say this vector field f is a function of u1, u2 and u3. As you have seen in the earlier lecture that any vector may be expressed in terms of the unit vectors in orthogonal curvilinear coordinate system, and so this vector field f may be expressed like this, that f is equal to f1 e1 hat plus f2 e2 hat plus f3 e3 hat. Here e1 hat, e2 hat and e3 hat, you know, these are actually the unit vectors along the three curvilinear coordinate axes. So, if f is equal to this much, then how the divergence of this vector field will be defined, we will see it here. In fact, divergence of a vector field f is also denoted by the symbol del dot f, or you may say that del dot operator is divergence operator. So divergence of f is denoted by del dot f. Now, since f is equal to this much, as you have assumed that f is f1 e1 hat plus f2 e2 hat plus f3 e3 hat, so when you will operate this del dot operator, that is divergence operator, on this vector field, what will be the result? You can see that del dot f may be written as del dot f1 e1 hat plus del dot f2 e2 hat plus del dot f3 e3 hat. Now, actually, to know the value of this divergence of f in orthogonal curvilinear coordinate system, we will evaluate all these three terms in RHS of this equation 1. So let us try to evaluate the first term, and when we will get the value of first term, just by an analogy, you will be able to write the expression for the other two terms in RHS of this equation 1. So let us try to find what will be del dot f1 e1 hat. So now let us consider it. So now del dot f1 e1 hat. As you have seen in the earlier lecture that this e1 hat unit vector, this is actually equal to what? This is equal to h2 h3 times del u2 cross del u3. You know it. Actually h2 h3 times del u cross del u3, this has been written at the place of this e1 hat, at the place of e1 hat. So you can say that as this e1 hat is equal to h2 h3 del u2 cross del u3. So we have replaced this e1 hat by this expression. Now let us simplify this result. That is, you can say that del dot F1 E1 hat, you can see this may be written as, see here, this is actually equal to this much, and this expression in RHS may be written as del F1 H2 H3 dot del U2 cross del U3, del U2 cross del U3. You may write it. Now let us simplify a little bit the RHS of this equation. This may be written as del F1 H2 H3 dot. As you know, in orthogonal curvilinear coordinate system, the unit vector E2 hat is defined as del U2 over modulus of del U2. You know it. And this del U2, mod of del U2 is denoted by the symbol H2, which is an scale factor. So del U2 vector may be simply written as E2, this is E2 hat, and if you want to know the value of del U2, what will be this del U2? In fact, del U2, this is a mod of this del U2, this is in fact 1 over H2. So this E2 is, so E2 hat, yes, this is 1 over H2, and this will be actually equal to H2 del U2. And so del U2 is equal to, in fact, E2 divided by H2. So instead of this del U2, you may write E2 hat over H2. And similarly, del U3 is equal to E3 hat over H3. E3 hat over H3. Now, in orthogonal curvilinear coordinate system, you know E2 hat cross E3 hat, this is equal to E1 hat. So this expression you may write like this: del dot F1 E1 hat, this will be equal to del F1 H2 H3, and E2 hat cross E3 hat, this is in fact E1 hat. So this is E1 hat over H2 H3. Now in the previous lecture on gradient of a scalar function in orthogonal curvilinear coordinates, you have seen what is the expression for this del operator, that is gradient operator, in orthogonal curvilinear coordinate system. You have seen it, and you know this del operator is defined like this. This is E1 hat over H1 del U1 plus E2 hat over H2 del U2, and plus E3 hat over H3 del U3. This is actually the expression for the del operator, and this is operated on this very function, that is F1 H2 H3. So this will be operated on H1 F1 H2 H3, and the remaining factor is dot E1 hat over H2 H3. H2 H3. So now you can see, after a little bit simplification, what will be our result? You can easily see here. This may be written as E1 hat over H2 H3, because in a scalar product A dot B is equal to B dot A, so you may write this second vector at the first place. So this may be written as E1 hat over H2 H3 dot. Now operate this operator on the function F1 H2 H3. So you may see this may be written as E1 hat over H1 del U1, and this will be operated on F1 H2 H3. You can see, plus the second term is E2 hat over H2 del U2, again F1 H2 H3, and plus E3 hat over H3 del U3, and this will be again operated on F1 H2 H3. F1 H2 H3. Now you know, in orthogonal curvilinear coordinate system, E1 hat dot E1 hat, this is equal to 1, but E1 hat dot E2 hat equal to E1 hat dot E3 hat, and these are equal to 0. So only the first term will remain non-zero, and the remaining two terms will be 0 when you will take the scalar product of these two terms by E1 hat. So you can see, after taking the scalar product with this E1 hat, this second term and the third term will vanish, and only the first term will remain non-zero. So what will be your result? E1 dot E1, that will be 1. So this will be simply 1 over H2 H3 times H1 del U1, this much. So you can write this now. Therefore you can say that del dot F1 E1 hat, this is the term in LHS, and this is simply equal to, you can see again here, this is H1 H2 H3 del U1 F1 H2 H3, because E1 dot E1 will be equal to 1. So this is 1 over H1 H2 H3 del U1 F1 H2 H3. Say this is your equation number 2. So you can see we have evaluated the value of del dot F1 E1 hat, but in equation 1 the other two terms are del dot F2 E2 hat and del dot F3 E3 hat. Now we will write the expression for these two terms, but there is no need to calculate these two terms independently, like as you have calculated the value of first term, because when we know the value of this first term, just by an analogy, just by a comparison, you can directly write the expression for the second term and the third term in RHS of equation 1. So See, you can say just similarly, what will be the expression for del dot F2 E2 hat? You can see subscript 1 has been changed by 2. 1 has been changed by 2. So wherever in this expression 2 there is 1, we will write 2 at that place. But the other subscript 1 and 3 will remain at each. So you can see in the light of equation 2, you may write the expression for del dot F2 E2 hat, and this will be what? This is 1 over H1 H2 H3 and del U2. Here there is del U1, so here will be del U2. And instead of F1, now we will write F2, and as 2 should be replaced by 1, so here will be H1 and H3. Say this is equation 3. Now similarly, you can write the expression for del dot F3 E3 hat. You can easily write the expression in the light of these two equations. This will be 1 over H1 H2 H3 del U3, and can you say what will be here? Definitely you can say this will be F3 and H1 H2. This is equation 4. So you can see we have evaluated these three quantities, and after knowing the value of these three quantity, when you will put the values of these three quantity in equation 1, you can see you will get the value of divergence of f. So now let us substitute all those values in equation 1. See the equation. This is simply the sum of all those three terms. So using these in equation 1, using equations 2, 3 and 4 in equation 1, we get what will be our result? You can see divergence of f, which is just equivalent to del dot f. What will be this? Sum of all these three equations. And as you can see that 1 over H1 H2 H3 is just a common factor. It is present in all these three terms. So you may take this 1 over H1 H2 H3 as a common factor. So this is 1 over H1 H2 H3. You know this H1 H2 H3 are actually scale factors, and the remaining terms will be del U1 F1 H2 H3 plus del U2 F2 H1 H3 and plus del U3 F3 H1 H2. And actually this is the expression for divergence of a vector function f in orthogonal curvilinear coordinates. This is the general expression. You will see the utility of this expression when we will deal with the divergence of a vector function in particular orthogonal curvilinear coordinates like Cartesian coordinates, spherical polar coordinates and cylindrical coordinates. Actually, when we will find the divergence of f in all those three orthogonal curvilinear coordinate system, you have only to evaluate the value of scale factors h1, h2 and h3. And when you will substitute h1, h2, h3 in this expression, you will get the particular expression of divergence of f in a particular orthogonal curvilinear coordinate system. But those things will be dealt in actually the forthcoming lectures.